Hello everybody, thank you for coming along today to our virtual tour of LIGO Minecraft. My name's Daniel Brown. I'm a researcher here at the University of Adelaide in Australia, and today we're doing a joint outreach meetup between OzGrav and LIGO India. Okay, so if you have any questions, then please do direct them to our Twitter question and answer session. You can use the hashtag AskOzGrav or hashtag AskLIGOIndia, and one of our researchers will hopefully get back to you as quick as possible to answer your questions. You can join in today on the Minecraft tour live if you wish, and you have a copy of Minecraft. You will need a version 1.16.3, and that will be the Java version of Minecraft. Unfortunately, we haven't got the Bedrock version ready yet. So if you're trying to play on mobile phones or any consoles, then I'm afraid you won't be able to join it this time. So hopefully you can all see this is a view of the LIGO Hanford detector, which is what we're based on. There are two LIGO detector sites currently in the world. There's one in Washington State in North America, and also one in Louisiana, in Livingston, the south part of the United States. And so we built this map to try and give people a better idea of the scale and the various parts that are involved in this fascinating experiment. So this Minecraft map was made by a group of us here at the University of Adelaide. It was made by myself, Daniel Brown, and a very large team of us, which included some master's students, other postdocs, undergraduate students. We also were funded by the South Australian Community Grant, so they kindly gave us some money to help pay for the server costs and developing this map for you all to play with today. So to start off with, we're just going to have a walk through the front door effectively, and when you come into LIGO, there's a type of conference area where lots of meetings happen. And as we go into this office area is typically where people work and do their research. So around this area we have various pictures and diagrams which we'll go through. This one here is what we want to talk about or bring to your attention today, and this is the first gravitational wave signal that we measured. It's GW150914, which happened exactly near enough to the day 5 years ago. So this is the 5th anniversary that we detected these signals. And what we can see here in this trace, in the bottom axis here, we have time. And you can see this is just in seconds, so this is a short fraction of time that this happened. And on the y-axis over here, we have strain. So this strain is like the amplitude of the gravitational wave that LIGO has measured. And here in orange and blue, we can see the Hanford and the Livingston data, and we can see how beautifully they match up. And we can see it starts off a bit slow here, and it gradually gets above the noise. It becomes faster and faster, and then eventually the signal disappears. So to better try and understand that, let's have a look at some more of these diagrams around here. So what are gravitational waves? Well, they're waves in what we call space-time. So this is, you can think of it in many ways as similar to waves or ripples on the surface of a pond if you have some moving object within it. And so gravitational waves are emitted by asymmetric masses rotating around each other, just sort of what we see here, which are these two neutron stars. And as these rotate, they emit these gravitational wave ripples that propagate all the way across the universe. And by and large, the gravitational waves are actually incredibly weak. And you need incredibly heavy masses to actually generate them in the first place. So you can't just simply get this by spinning around in your house. You need something heavy like black holes, neutron stars, and incredibly violent events that are sort of astrophysical events that are associated with them. And so the type of this waves that we're actually getting is not like you would probably imagine a wave on like the ocean or surface of a pond or such, but it has this kind of very odd, unusual undulating shape as shown in this diagram here. And we can see what happens, if you imagine that we were stood in this final circle over here, we were sort of stood in the middle of it. This is the space and time in which we exist. And so as the gravitational wave comes through and it passes through us, we get squashed horizontally, and then we get stretched vertically. And then in the opposite direction, we then get stretched horizontally, and stretched vertically, and then squashed horizontally. And so we get this kind of stretching and squashing motion, which is what we're trying to detect. So the type of events that we might see are things like these neutron stars here. As gravitational waves are emitted, the energy is kind of sucked out of this astrophysical system. So as we radiate more and more gravitational waves, these neutron stars or black holes get closer and closer together until it gets to the point where they then touch and merge. And in the case of neutron stars, we would typically expect there to be something like a supernova or other violence explosion that come with it. And as we can see here, here's all the cloud and the debris that's being emitted. Of course, for black holes, which we could see down here at the other end of the corridor, these are just orbiting around each other as such, but there's no sort of matter to speak of really the way here where they're going to, there's no accretion disks and such. So when they collide together, there is nothing we can see. It's just dark. The only way we can see these black holes crashing into each other somewhere out there in the universe is through gravitational waves. And so this is what this signal is showing us. So here, GW 150914, first one we measured, basically pretty much as soon as we switched the advanced LIGO detectors on. We see gradually here they're spinning, and as they get closer and closer, the waves start getting stronger and stronger, and eventually, as they release their energy, they also start rotating faster, and then eventually they collide here, and we get this merger. And of course, after this, we just have one black hole, and this is just the remnants of these two that have collided together. Unfortunately, our image seems to be rotated here, but this here gives an idea of the sort of where in the universe these come from. And just like if you have, we have two ears, we can sort of pinpoint where some sound is coming from, because gravitational waves, in a way, are much more akin to us sort of hearing the universe, rather than if you had a telescope, like an optical telescope, you're seeing the universe. With gravitational waves, we're very much listening. And the more detectors we have, the better idea where we can sort of pinpoint where in the universe these, or where in the sky, and at least where these sources are coming from. And as you can see here, we have these big orange sort of contours and blue contours. These are all related to different signals. As you can see here, GW 150914, for example, and there's a big area. If any of you have seen the Milky Way at night, you realise that this is an incredibly large area in the sky. And of course, to then say that two black holes crashed into each other somewhere in the universe out in this rough direction is a lot of space to look at. And it was a similar story with some of the other detections we made. But gradually, as we build and switch on more and more detectors, we end up being able to pinpoint exactly more precisely where this has come from. So you see from GW 170814, for example, this area is starting to get much smaller. And so now we have the two LIGO detectors, we have Kagra and Virgo, they're running along, and they can help pinpoint this better. And of course, hopefully in the future, once it's all up and running, we'll also have LIGO India. So how does LIGO actually detect these waves? As we kind of said over here, it's this sort of stretching and squashing of space. But how do we do that? I mean, if we just stuck a ruler down, this would just get stretched and squashed as well. So instead we use light. And here is a very basic sort of animation showing us how what we call a Michelson interferometer works. And this is the basis of the advanced LIGO detectors and pretty much all the ground-based detectors that exist today. And so here we have a laser. We have a beam splitter, and this laser travels to the beam splitter. This beam splitter splits the beam in half. It sends half the light up what we call this arm here, and then half the light across this horizontal arm. At the end of these arms are two mirrors. The light is then reflected back, and it travels back down to the beam splitter, where it will recombines. As you can see from this animation, and these waves at the top here, depending on how long or stretched and squashed these two arms become, the waves either become in phase or out of phase. And when they're out of phase, this wave will add up and cancel each other out. And obviously there's no light, we don't see any light. And as soon as we see the length of these arms change, we get pulses of light come out at the end. And so this is effectively what a gravitational wave detector is doing. It's changing this stretching and squashing of space and time into flashes of light, with laser light, that we can then pick up on a detector and measure. So advanced LIGO is a bit more complicated. We'll explain these as we go along. We'll also have a quick look here about where the current location of some of the ground-based detectors are. So we have Kagura in Japan, LIGO India, Virgo Geo 600, Hanford and Livingston over in the US. So this is the office primarily where all the researchers work. People who are visiting will grab a desk and get on with their research. And as we go through this corridor, we come to the other side, we come more towards the areas of where more of the engineering and running the detectors happen. So down here on the left we have the control room, which we'll have a look at in a second. But first of all, we're just going to take a sort of a quick flyby, or flyover of the detector, just to get a scale of it. So when we built this map, we tried to build it to scale. Here we have what we call the LVEA, which is the corner station. So this is the beam splitter part of the LIGO interferometer, where the laser's generated, for example. And then here's where the office building where everyone works. And so we're just going to take a fly down to what we call the end station. So the LIGO model itself is not, the Minecraft model itself isn't exactly 4,000 blocks long, because that's just a little bit too long. But here we're reaching the mid station, which would be 2 kilometers away from the corner station, and then as we carry down, we then eventually get to what we call the end station. And so this is the end part, 4 kilometers away, where we house this end mirror. So light will bounce all the way from the end station, all the way up down this tube, reflect from that mirror, and bounce all the way back in. And so in this concrete tube, we have a very long vacuum enclosure. And so for the light to just travel down 4 kilometers of air, the light will get absorbed, it will get scattered, it will be lost effectively. We won't be able to operate the interferometer. So instead, what we need to do is put this into a vacuum. So effectively, in this steel tube that travels all the way along down this arm, and all the way up the other arm, is all the air is completely evacuated. It's an ultra-high vacuum system, and the laser light can then propagate freely all the way from the central station all the way to the end station. And this has to be sort of protected by this concrete enclosure. This just sort of protects the tube from any sort of damage from the environment, etc. And as we will see shortly, flying seems to be very slow. As we get to the down here, we'll be able to see some more details about why, for example, it needs to be protected. So, for example, the Hanford detector is actually quite near a nuclear power station in the Washington state, and there's a police force that obviously patrol this area. And LIGO Hanford is basically a very large sort of deserty area. But then one day, I think, someone probably didn't realise that just over this mound was a big concrete wall, but over the car came and straight into the side of the vacuum, sort of this concrete tube to protect it. Obviously, if that wasn't there, then it would have been rather catastrophic, and we probably wouldn't have LIGO as we know today. Another thing you may have seen in many movies, in sort of desert films, these tumbleweeds. And so tumbleweeds, I imagine, are sort of in this desert environment where there's not much going on, and you might see one tumbleweed blowing all out around. But LIGO Hanford seems to struggle with this a lot. They're everywhere. And as you can see here, here's some poor person who's having to try and clear up the amount of tumbleweeds that have been blown over, obviously in a storm or something, and these are piled up much higher than the car, for example. And again, here we can see a whole corridor of tumbleweeds. So of course we can't put them. We have some here scattered around, but luckily we don't have too many. So we're going to take a fly back in now. Go back and have a look a bit more detail at the control room. Yeah, there we go. Follow that. So okay, so welcome to the LIGO control room. As you can see, there are lots of screens going on, and this is pretty much where most people will sit trying to run the detector, keeping an eye on it, making sure it's all operating correctly. Here and over in this corner, I have what's called the operator station. So here, during science mode, when the detector's actually sat there, what we call this low noise state, listening out for potential signals coming in, there will be a person manning this station 24/7. And they'll be in charge of looking after the machine, making sure that things are running correctly, checking all the various different parameters, listening for alarms that might go off, and if there is a problem, making sure that we get the right help in. So these screens are actually for fairly recent snapshots that we've taken from the LIGO Hanford control room. So these are the actual screens that you would see if you were there at these particular times. This plot in the middle here is probably one of the most important ones. This shows you what the current sort of sensitivity level of LIGO currently is running at. And so this red line is what LIGO Hanford was operating at the particular time that this was taken, which was the 22nd of July 2020, so just over a month or so ago. This yellow line and blue line, which you can see here, are actually the sensitivities that we're running at in the last run. So you can see here we're running at about 119 megaparsecs on February the 6th. This is also the sensitivity from LIGO Livingston in blue. As you can see, the range of which we can potentially hear two neutron stars colliding in together from is slightly larger at Livingston. It's 140 megaparsecs away. And so here is this blue line here. So you can see there's just this very slight improvement. So the lower this curve is, the more sensitive the detector is, and the more circumscribed measure. You can see the small difference here in these two lines results in 20 megaparsecs further away that we could hear potential collisions from in the universe. So a lot of the aim of the game here for LIGO gravitational wave detectors is effectively make this sensitivity curve as low as possible. We do that by trying to remove sources of noise, fixing, installing sort of upgrades to effectively make the instrument more sensitive. There's a vast array of information around in the control room as well. One thing that is very problematic for many ground-based detectors is obviously earthquakes. Obviously we're trying to measure a gravitational wave here, which is it changes the length of those two arms on the order of 10 to the minus 19 meters, which is 1,000 times smaller than the size of protons in this tiny distance. So of course the big challenge in LIGO is isolating it from the environment. And one of the biggest of those is actually earthquakes that might come in, or if you've got a particularly large storm, for example, that's in the Pacific, bashing up against the west coast of America, then those seismic waves will then ripple through the continent, get to LIGO, and shake the mirrors enough that they become problematic. What we can see here, for example, is actually quite a reasonably large earthquake that's coming. And we can see that something's happened. The seismic motion has suddenly jumped up very high, and then it takes several hours for this to decay. And LIGO can be disturbed by large earthquakes from all over the planet. So if they happen in Papua New Guinea, South America, all over the place. So you obviously get a lot coming from the ring of fire around the Pacific, and as those come in, they will start shaking the detector too much. We also suffer from, for example, sort of what we call anthropogenic noise, trucks, wind, and all this stuff. So we have different seismic sort of frequencies in which trouble LIGO. So we have the low frequencies from big earthquakes, for example, but then you can also have just the daily hustle and bustle of normal life. As more people are driving up and down the road near LIGO, big trucks going past, if it gets too windy outside, etc. All these sort of things can add to the total noise that's happening. This screen over here gives a very sort of brief overview of what's happening in the detector at the time. And so at the moment, this will tell you how much laser power is being generated. This tells you how much is actually going into the interferometer. So at this moment in time, this was taken when the interferometer was actually off. And if something's gone wrong or something needs looking at, the operator can quickly look at this screen and see, for example, here's some red. Red things typically tend to be bad. Green is normally good. So anything is red, someone should probably try and take a look at it. One other interesting point to note, because it's a worldwide collaboration, the LSE, we obviously need to keep time with everybody. Obviously we're here in Australia and it's now 3:52 p.m. It'll be a different time in India. But to save confusion, a lot of the times we make sure we try and use what we call GPS time, which is this clock up here. And if you're used to dealing in gravitational wave signal and analysing some of the data, you'll notice that they all come along with this sort of large number. So this is the number of seconds since GPS was switched on. And so this provides a good reference for which all of us all over the planet can use. GPS is everywhere. So when we say that something happened at this particular time, then we can all agree on what time that happened. So let's go and have a look a bit more at the engineering parts. As we go down, we have one of our resident scientists sitting here working in Minecraft. Here we have a computer room where everyone works on various computer tasks. In here, obviously, a lot of the LIGO is run and controlled by automated computer systems. Obviously, this is not something that can be done by hand all the time. So there are a vast array of controls and machines all looking over the LIGO. There's electronics rooms in here. And then further down the hall would be mechanical workshops. We also have a great picture here from, obviously, our Nobel Prize winners. So in 2017, sort of Ray Weiss, Barry Barish, and Kip Thorne won the Nobel Prize for the detection of gravitational waves. But here for LIGO, we have the LIGO Scientific Collaboration. And so there's a lot of people that have worked on these detectors over the years, and this is hopefully a semi-recent, and hopefully includes everyone, update of all the different universities from all over the planet that work on this. And so it ranges from all over the world, and there's about 1,000 of us, or 1,000 or more probably now, that work on this detector, from data analysis to the experimental side, to make things, keep things up and running. So normally if you would be on this tour, you can actually go visit LIGO, and you can go and actually see the site, and I think once a month they will run a tour for everybody. And normally you'd follow this corridor out and then go off to the left, and you'll be outside, you take a nice view of the outside. Obviously you can't have lots of the members of the public traipsing through all the clean room areas, but of course in Minecraft LIGO we can go and have a look around inside to get a better idea of what's actually in there in LIGO. So of course this is the clean room area. Here we have a boot scrubber which you have to shove your foot in and run it to scrub all the dirt off. And as we go through, this is the area where we start getting what we call garb dump. And so we end up becoming, stop all the dirt that effectively we're carrying in on Earth to getting into the instrument, because we need to keep this place ultra clean, ideally. Because the instrument isn't necessarily dangerous to us. It's more that we're dangerous to the instrument. We leave behind hair, bits of skin, dust, mud, all sorts of stuff, which is not what we want inside the actual interferometer. So normally you get dressed up, depending on what kind of area, what kind of work you're doing, into this what we call clean room garb. There'd be clean room hats, masks, which I'm sure we're all probably wearing more of nowadays, clean room sort of overcoat, gloves, and then little buoys down here to make sure if you're wearing shoes that you've worn outside the clean room area, to keep the dust off. So around the back here we have lots of laser labs, which if you want to go in and explore yourself, if you want to, if you have Minecraft, you can have a look around there. And there's optics labs where various bits of equipment are tested and put together just before they're actually taken out into the sort of main, what we call LVA. Here we have some more scientists hiding up on top of boxes. Not quite sure why they're like standing on top of things so much. But as we come through here, we get into what's called the LVEA. So the laser vacuum enclosure area. And so this is the main part in the central building that houses the main aspects of the LIGO detector. So down here on the left is what we have called the PSL, or the pre-stabilized laser. Pictures are jumbled up again. Here we have this is where the laser is generated and fed into the interferometer. And here we have three jumbled looking scientists working on setting this up. And so in this area, as this is a high power laser area, there's separate clean rooms. Once you've gone through that initial clean room, then you have to go and get cleaned up again before you go in, because high power lasers and dust do not agree very well, end up blowing up and making smoke and a lot of dirt. And so what will happen in this area is the laser will be generated, and it will then be shot into the actual vacuum systems. And so this is the beginning of the laser's journey into the interferometer. There we go. And as you can see, it shoots off down there. And as it goes in, it will hit more optics and begin its journey through the LIGO interferometer. So as we come down here, we see that we have various big tubes which the laser travels down. Then we get to these sort of larger areas here, vacuum systems here, which is where we house sort of specific parts of optics. And so these are called ham chambers or horizontal access modules. These are sort of big vacuum systems which are effectively like two doors on each side. So these parts can be removed, which we'll see in a bit, and then give access to. So as we come around here, we get to ham 3, ham 4, for example. There's lots of ham chambers. Here's a picture just to give you a bit of a sense of scale and idea of what we've created here in Minecraft. So here we can see the big vacuum tubes. I believe this is going out to the Y-arm. And in the part here we can see all the various tubes and systems. So you see these blue piers here. This is what we call HEPI, which is the hydraulic external pre-isolation system. And so this is, as I was saying before, in the control room, seismic motion, waves coming in is like one of the main concerns that we have. And to get rid of this, we basically have to isolate it by making complicated suspension systems to protect it. So this is the first stage in this isolation system. We're trying to isolate this whole system from the seismic motion. And these vacuum systems are effectively placed on these blue HEPI piers and struts. So as we come down, we can see a picture of what's actually inside what we call one of these hams. And so these hams are pretty big. We can just nearly about fit a person in there. And inside here, we can see all the various optics that are then bolted to these tables inside here, or the RSI, or initial seismic isolation platforms. Here, actually, for those who might be interested, I believe is probably ham 5, I think, and this is probably the output Faraday. And this is probably the signal reciting. So as we go down, we then come to the final part, which is actually where the gravitational wave signal comes out, and this is called ham 6. And this is where the laser light will finish its journey. It will go, the gravitational wave signal will come out of this part here, hit a photodiode, and be read out into computers. So following around here, we can see an example of two of our fellow Australian researchers from the Australian National University, and this picture was taken fairly recently, last year, when we were over there installing upgrades to the Advanced LIGO program, the Advanced LIGO detectors, to install what we call a quantum squeezer. And so LIGO is actually limited by the quantum nature of light, what we might refer to as shot noise, and we can use quantum squeezing to effectively circumvent that by effectively putting more noise into different, what we call quadrature of the light. And so that enables us to significantly increase the range of our detectors. So as we come in, we can see we've got some open tanks over here. We also have these big clean room tents. So even though we're in a semi-clean area, we also have clean room tents that are hung over the open chambers just to make sure, double check that no dirt or dust will get in there. And here we can see what we call the input test mess. And so this is the one of the mirrors that form what we call an optical cavity. So LIGO isn't just a simple Michelson interferometer. It's constructed of many more mirrors. And this is basically just to ensure that we can get a build-up of the optical power. So what we want to do is we send in 1 watt of laser power, and then we make what we call an optical resonator that traps the light in between it. And this resonates or bounces around and around and around, up and down the arms multiple times, and it allows the laser power to build up. And so in the end, we end up storing, hopefully once we get to design, what our design power levels are of nearly 750 kilowatts of laser power inside each one. And so this starts off by this input test mass, and then a similar suspension stack will be hung up here. So if we follow around, we can sort of go up. Oh, somebody's got stuck in the laser. So as we go over the top, we can sort of, as obviously there's big tubes, so there's these big nice sets of stairs to let us sort of get over and access the various different parts of the LVEA. Here we can go and get a better idea of what these test masses actually look like. Here, for example, we can see another level of suspension. This is what's called the VSC ISI, which is the suspension systems that are installed in the top of each one of these big chambers over here. So each one over here, as we just saw with the test mass, the test masses are all hung from each one of a seismic platform that looks like this. And I should also say that this is they're suspended not by what you might imagine is as a steel wire and things like this, which were used in earlier versions. These are actually sort of suspended now by. I just broke a hole in the picture. These are actually suspended by the thin glass fibers. So we have 40 kilogram test masses, and then these are suspended either side by 2 thin strands of glass. And these end up holding up the 40 kilogram masses. And so we do this to ensure that we don't get as much loss, effectively. So as those glass fibers bend and move around, and the thermal properties of them are much better than if we were just using something like steel or steel. So here we get a better picture of what the actual sort of suspension looks like. This cage around it is actually just there as a protection, just to catch it in case one of the fibers break. And the fibers do break. If there are, for example, a very large earthquake, that might cause it to break, or if it's something that gets knocked, or just maybe a natural failure in the glass fibers. These are there just to catch it and stop it swinging too far and becoming damaged. So here we have one of the test masses, which we can get another nice picture of here. And so these are some of the best test pieces of glass made in the world. And we have multiple of them required in LIGO. So we have one at this end, another at the other end, this arm, and then there'll be a similar one in the other arm system as well. So as we go over, we can start going down, and as we get to this part, you'll notice that what I described before as a simple Michelson looks slightly more complicated here. So what we actually have here at the Hanford site, at least, is actually the remnants of another interferometer. So there is H1, which is the 4-kilometer Hanford detector, which is still and exists there today. But there was also, at some points in the past, H2. So H2 was actually a 2-kilometer detector, which was actually run side by side with the 4-kilometer version. And so now this no longer is used and is actually being dismantled. And parts of this will go to LIGO India, and parts of it will also be used for the what we call the A+ upgrade, which will be happening soon to the LIGO project. But over in Hanford we also have a big area, and this is where a lot of the parts of LIGO India are currently being stored and will be shipped over. So for example here we can get another overview of the LVA, just for scale size. Here's a person, there's these big cranes that help lug everything around, and all these various different parts here are parts that will probably be shipped over to LIGO India, Another picture just to get a scale of these things, like how big these tubes actually are. They are really about 2 meters in diameter. As you can see, someone is in here in clean room. This is the full clean room, what we call bunny suit, which is to try and keep this area super clean. Because this is where all this area will be turned into a vacuum before we can actually operate in low noise. And this scientist engineer here is actually installing what we call a baffle. And so what we install are these big kind of ring features that go around these tubes, and this stops stray bits of laser light from getting back into the sensitive interferometer. So hopefully we can improve the sensitivity further. So I hope you've enjoyed this this tour of Minecraft LIGO. Hopefully it's given you a better appreciation and idea for the sort of the scale and the size of LIGO and the various different parts of it. You're more than welcome to ask us any questions on Twitter or YouTube channel. or if you're in Minecraft, you can also just type up in the chat here and we can get back to you. But please do feel free to log in yourself and actually explore this place. There's various parts that we haven't shown, and there's various rooms that you can go and explore and get more details about what's actually happening and what parts of LIGO there are to see. So, thank you all for coming.